Welcome students to this another session on industrial metallurgy. This is session number 31 and let us see what all we are going to cover in this session. Basically, we'll start with the next type of binary alloy systems, type 3, which are again referred to as eutectics only. For an example, we'll take the lead tin system and finally we'll give you the labeled lead tin binary equilibrium diagram along with the eutectic reaction details. You see binary alloys in which the two constituent elements which are forming the alloy show 100% liquid solubility but show partial solid solubility are type 3 binary alloy systems. And students, in fact, these are the most popularly observed and most popularly used alloy systems. So to explain the equilibrium diagram of type 3 binary alloy systems, the example of lead tin alloys would be taken. Commercially, these alloys are very useful because of their low melting point, right? And high resistance. They are used as a soldering material. So whenever you see a PCB being soldered or any other electrical circuit being soldered, no wonder on most occasions it would be a lead tin alloy which has been used as the soldering wire. Also in fuse wires, which are used for safety purposes of electrical circuits and electrical equipment, these lead tin alloys find wide application. They are also used as tournay plate, as coating on steel surface to prevent its corrosion. So this is a very low cost, low melting point, very useful commercial alloy. And let us see how does its equilibrium diagram looks like. But before that, again, these systems are eutectics. I've already discussed in earlier sessions as to why a particular alloy system is called a eutectic. Number one, if that alloy system undergoes eutectic reaction, and number two, any alloy system whose alloy series always contains a special composition, the eutectic composition, which melts like a pure metal, which solidifies like a pure metal, even being an alloy. That is the second reason why a particular alloy system is called a eutectic. So for these reasons only, type 3 binary alloys are also called eutectics. In type 3 binary alloys, the eutectic temperature is 183 degrees centigrade, and 61.9 percentage tin alloy is the eutectic composition. So this shows the labeled lead tin equilibrium diagram. We have pure lead on this side and we have pure tin on the other side. So we have zero tin here and we are increasing tin content from left towards the right. So this alloy is 60 tin and 40 lead, and just beyond this composition 61.9, this is that special composition, the eutectic composition. And students, this composition would show the eutectic reaction at the special temperature 183, which is the eutectic temperature for the lead tin alloy series. So here in this diagram you can see that this line ABC is the liquidus line. So whenever any lead tin alloy is at a temperature above this line, it always have one phase in it, the liquid solution of lead and tin. And here on the left side we have solid solution alpha. This is a solid solution with lead as the solvent, who has dissolved tin in it. So tin is the solute. And what is the maximum amount of tin that this alpha solid solution can accommodate in it? The maximum amount of tin that alpha can accommodate in it is 19.5. So alpha is a solid solution of tin in lead. Tin is the solute and lead is the solvent, and the maximum amount of tin that can be accommodated in this alpha solid solution is 19.5, but this happens at a special temperature of the eutectic temperature 183 degrees centigrade. Similarly, if you go on to the right side of this equilibrium diagram, you again find a single phase region which is called beta. beta solid solution. Beta solid solution is largely tin. So this has tin as the solvent and has got lead as the solute. What is the maximum solid solubility of lead in tin? You see this gap is 2.5. So the maximum solid solubility of lead in tin is only 2.5%, and again that is happening at this special temperature of 183, which is the eutectic temperature of this alloy. So students, there are three single phase regions: this liquid solution, this alpha solution region, and this beta solution region. And no sooner you have filled the single phase region of any equilibrium diagram, it becomes very easy to fill the other phase regions like two phase regions and three phase regions. So if I come to this region has got liquid from this side and has got alpha from this side. So this is a two phase region containing a mixture of liquid solution and alpha solid solution. Similarly, this region will have liquid from the left and beta from the right, and this region will have alpha from the left and beta from the right. So there are another three two phase regions: this and this. And finally we have a single three phase region here where all three phases are coexisting. So this point B can be referred to as the eutectic point. At the eutectic point, you have three phases coexisting. One is liquid, the other is alpha, and the third and the final is beta. Something new that you see in this type 3 systems clearly, which you saw in the corrected and modified type 2 systems, let copper, this bismuth cadmium alloy also, is students these lines. See, this is the liquidus line ABC, this is the solidus line ADBEC. Liquidus line signifies that anything above me is in a pure molten state. Solidus line represents that anything which is below me has to be in the solid state. And these two lines are newer lines which we haven't discussed as of now in our discussions on this subject of industrial metallurgy. Students, this line is called the solvus line. This line is the solvus line. So D, F and E, G are solvus lines. Mind it, what is the uh, mm, significance of the solvus lines? Just a while ago I said alpha is a solid solution with tin as the solute and lead as the solvent. What is the maximum amount of tin that can go in alpha solid solution? 19.5. Now if you start dropping the temperature, what you will realize is that the, see, who is telling us about the chemical composition of alpha solid solution? This line. Who is telling us about the chemical composition of beta solid solution? This line. So when, suppose you have any alloy and it is at this temperature, say the eutectic temperature, alpha contains 19.5 tin in it, beta at the eutectic temperature contains 97.5 lead and solute sorry, 97.5 tin. So that means solute, that is lead, is only 2.5, and this is at 183 eutectic temperature. Maximum tin that alpha can contain and maximum lead that beta can contain. But alpha and beta will not continue to keep on will not continue to contain these maximum amounts of solutes in them. As the temperature drops below 183, you will see alpha will precipitate uh, tin out of it. Here it is 19.5, but here at 0 degrees centigrade, what is the amount of tin in alpha? It's only 7%. Somewhere over here it's only 8%. So it is this line which is showing the change in the solid solubility of tin solute in alpha solid solution. Similarly, this line is showing with change in temperature the change in the solid solubility of lead solute in the beta solid solution. So these two lines are called the solvus lines. So what is a solvus line? A solvus line is a line which tells change in the solid solubility in the solute of an alpha solid solution when with any drop or any change in temperature. Okay, then students, this is a eutectic system. Type 3 are also eutectic systems, and let's specifically now see that how does the eutectic reaction take place in specifically this lead tin alloy. So in lead tin alloy, as you are cooling the alloy, and when you reach the eutectic temperature, which in case of lead tin alloys is 183 degrees centigrade, liquid solution of eutectic composition will definitely be present. and this liquid solution present at the eutectic temperature during cooling will undergo the eutectic reaction and will transform to two new solid phases, the new solid phases being alpha of maximum solid solubility and beta of maximum solid solubility. So you can see alpha is formed of maximum possible solute 19.5% tin, and beta also formed is of maximum solid solubility of solute 2.5% lead, and this whole is called the eutectic mixture. And in this eutectic mixture you can also find out that what is the relative weight ratio of alpha is to beta, and that's nearly about 1:1. 54% is this and 45% in this. This whole is called the eutectic mixture and would always get formed as a typical alternate lamellas of alpha and beta would be there. I hope you have understood all the things that I have tried to explain to you in this particular session. So in the next session, we'll do the classification of the lead tin alloys, and we'll also talk about the equilibrium cooling of each category of lead tin alloys. I enjoyed this session. I enjoyed making this session for you. I hope you'll also enjoy as you watch this session. Thanks so much. Thank you, students.